Okay, so yeah, so ignore the email that says we have our next topic on the 18th. So that should be 13th. And I've corrected it on the announcement. So it was saying 18th here before, but it's not 13th, okay? So today we're going to finish up confidence interval. Just one concept remains essentially, but we'll just go through, kind of the previous concepts and make sure we pick up. So this is just the concepts that we're going to pick up. So I hope we'll be able to cover a lot of grounds today, like work some more questions. I have compiled these ones to cover the new concepts and some of the questions you sent. So I think maybe we'll just start with that, and we'll come back to the PowerPoint to continue. Okay. So this is coming from section 6.2, and this particular question. So we'll just go through it. So it says, suppose the age that children learn to walk is normally distributed with a mean of 13 months and standard deviation of 1 month. I wish that would be a different number, but it's okay, we'll work with it. 12 randomly selected people were asked what age they learned to walk. So write the answers to 4 decimal places. So the first question will be, how is X distributed? Change this color. I want you to pay attention to the two different questions. So A and B is very similar, isn't it? But the only difference is that B had to do with central limit theory, right? So let's take care of A, then we'll come back to B. So data, if you just collect your data when presenting with X, right? If you find the mean of your data when presenting it with X bar, right? So ordinary data is normally distributed, is the notation, as the mean and the standard deviation. So this tells you the distribution, like how spread out the data is, ordinary data. But if I take a sample of mean and get so many of them and I plot a histogram with it, it is distributed normally also with a mean, mu, but the standard deviation changes, right? It's distributed as standard deviation by square root of n. Okay, this is actually called the standard error. Size that in the next section. So standard error is standard deviation divided by square root of sample size. So this is correcting for the size of the data you have. And that is the central limit theorem. Okay, so for central limit theorem, the mean remains the mean. Doesn't change. But the standard deviation changes to the standard deviation divided by square root of n. So to answer question A, you're going to be using this. To answer question B, you're going to be using this, right? Any other thing that led to question B, we're going to be using this one. All right, so A is simply saying, what is the value of the mean here? Right? What is the mu and what is the standard deviation? That's what A is saying. So here, we know from this question that it says, the mean is 13, so we know the answer, right? And the standard deviation is 1 month, so we know the answer. For the second part, that is where we apply the central limit theorem. Okay, and again, we just emphasize that the mean is still the same. If you are looking for the distribution of the mean itself, the distribution of the mean itself will still be the mean 13. But the standard deviation will change according to this notation here, right? Standard deviation will change to standard error. So we're just simply going to say, okay, what is our standard deviation? It was 1. Okay, let me write it over here. So you have the standard deviation divided by square root of n. So our standard deviation is 1. So we have 12 data points. 12 randomly selected people. So you divide this by 12. That's what gives you the result that you put over there. Please help us with calculator. What do we have? 1 divided by square root of 12 to how many decimal places are the question? It should be somewhere there. Okay, 4 decimal places. So please give us an answer to 4 digits.
0.2887.
0 points, right? It's okay, 0.2887. Thank you. All right, so that is the answer to that question. So if you have any other question relating to B, then the standard deviation I'm going to be using is 0.2887. If you have a question relating to A, you are using 1, right? So let's go down the list. Question C says, what is the probability that one randomly selected person learn to walk between these 8 number of months, right? 12.5 to 13.5. So pay attention to the difference between that question and the next one. So C says, what is the probability that one person randomly selected? D says, for 12 people, what is the probability that the average age that they work is between the same number? So question C and D is asking you the same thing, right? The question C is saying for one person, what is the chance that the mean lies between 12.5 and 13.5? And question D is saying for 12 people, what is the chance that their average time to work lies between those, the same two, right? Okay, so let's go ahead and take care of this. Okay, this seems we are not going to be messing up today. So let's move it on. So let's go ahead and look at question C. So for C, you can imagine a distribution like this one, right? Mu is in the middle, of course, and here we know the mean is 13. 13? Yes. So we know the mean is 13. Okay. And we know the standard deviation is 1. Okay. And the question is saying, what is the chance that you have a value between 12.5 and 13? So if this is 13, 12.5 should be on this side. That's good. And 13.5 should be somewhere. So what is the probability? And we keep emphasizing, right, that probability is simple as area, is simple as percentage, simple as proportion, they are all the same thing. So the question has said, what is the probability? The question says, what is the percentage? The question says, what is the proportion? We are all asking the same thing. We are after the area on the shaded space. So we're looking for this space. So one way to solve this, because of we're using table, okay, so deliberately we want to use table to do this problem and not calculator, right? Because the calculator will hide the processes, table will help us kind of see everything. Okay, so one way to do it is to look at it in 2 parts. Your table is left cumulative, right? If you go to the table, it starts from the left, cumulate to the right. So one way to solve this question is to say, okay, let me find the bigger area from the left. That will be this one, right? So this is 13.5. And this is 12.5. So let's find 13.5, the area cut off by Z value of 13.5. I mean, sorry, by the data point of 13.5. That will be the area here, all the way. But you don't need all of that, right? So let's say you match this with this. Let's say you match this with this, right? You don't need all of that. What you need is area that cut off at this point. So you need this middle section bounded in red. Right. So again, because we are using the table that accumulates from the left, so one thing I can do is to say, okay, what about if I find the remaining area on the tail? So what about if I find the area here? Right, and this is the 12.5 point. So if you call this I, call this I, you see that if you subtract I from I, you're going to get, so let's call this the main question. You're going to get the main question, right? If you subtract the area here, I from the area I, you're going to get back the main area. So what we simply need to do then is to say, okay, to go to the table, I can't find this data point. I can't find 13.5 because 13.5 is in months, right? So I want to change these values, these months to Z value, and then go to the table to pick up the actual value, right? So for the first part, the Z value for 13.5, given that the mean is 13, divided by the standard deviation of 1, right? Should give us 0.5. Is that, yeah, that is positive, right? For the second part, the Z value here, given 12.5, and that the mean is 13, divided by standard deviation of 1, should give us negative 0.5.
Sorry.
Right? Okay, we are doing all this thing knowing that for Z, the formula is your data points minus the mean divided by standard deviation. So that's what we're implementing. So let's then go to the table and look for, we're interested in two values. We're interested in the area covered by Z of 0.5 and the area covered by Z of negative 0.5 to the left tail. Right? So we see that the area for Z of 0.5 will be equal to, let's go to the table. I put up one earlier, or the normal table, right? So we're looking for positive 0.5. 0.5. So that is the Z value of 0.5. So over here we have the Z of 0.5. There is no decimal place, so we're just going to stay with the first one. So we have 0.6915. Okay, so let's go back to the question. So the area we have here is 0.6915. Then we go for the second one, the area that is for Z of negative 0.5. I'll go back to, excuse me, to the table. We're looking for negative 0.5. It's going to be on the negative side of the table. So we have negative 0.5 here. And again, there's no decimal place, so we're just going to remain with the first one. So we have 0.3085. 0.30. So bear in mind that we are calculating area. So there's no way this answer would have been negative, right? Because you're looking for shaded area. You can't have negative value. Right? So once you've gotten to this stage, the answer you need, the area you need, or the probability that you need will be what you will get if you subtract the area for Z of 0.5 minus the area for Z of negative 0.5, right? So if we do that, we have 0.6915 minus 0.3085. We subtract these two. Can you please help us? We calculate what do we have?
0.383.
0.383. Okay, thank you. Anybody getting something different? All right, so that is simply the area between those two spaces, right? That is the area between the shaded portion on this diagram that we titled main. Any question on this one? Okay, so I perceive that this will not be the issue, like I know we walked through this several times. So maybe the second question will be where the problem will come up, right? So the second question says, that is question D, sorry. It says, for 12 people, find the probability that the average age that they learn to walk is between 12.5 and 7 value, right? So because this question is talking about 12 individuals together, the previous one was talking about just one person, right? So because it's talking about 12 individuals, so we are interested in the average age falling between that space. So we're going to use the central limit here, right? So the only difference between how we solve this question, how we solve question C and how we're going to solve D will just be that instead of using the standard deviation as 1, you're going to be using the standard deviation as 0.2887. But that is the one that applies to central limit theory, right? That is the distribution of the average values, which is what the question is asking us. Okay, so, but every other thing is going to be the same. So let's do that very quickly. So again, we're going to have the same diagram. Let me pick another color. Maybe purple. So let's say we are on question D now, right? It's the same diagram, right? The same drawing. So the mean again is still 13. That does not change. Okay. I did not change. Right. So you have 13 there, right? And you're looking for the area between 12.5 and 13.5. You're still looking for this area, just as before. But the only difference this time is that the standard deviation you're going to be using will be the standard deviation you got for the central limit theory for the second distribution, because they're asking you questions that relates to central limit theory. So we're going to be using 0.2887. So right here, we're going to be using 0.2887 as our standard deviation. Every other work is the same. So we're just going to do it quickly. Again, we're trying to find the Z equivalent of these 2 points. So we can find the area using the table. So Z of data minus the mean divided by standard deviation. And that will give us Z of data here is 13 points. So what I'm doing, let's call this Z1, call this Z2. So we are doing Z1 right now. So 13.5 minus the mean divided by the standard deviation, which will now be 0.2887, right? Before we're using 1. So please help us find the value of this one. So that will be 0.5. Yes, divided by 0.2887. Would that be?
$1.7319.
1.7319. Thank you. Anybody having a different value from that? Okay, so we go ahead and do Z2, right? The second value there. So Z2 again, applying the same formula there will be 12.5 minus 13 divided by 0.2887. So essentially, we are looking for negative 0.5 divided by 0.2887. Okay. Of course, with this one too.
Negative 1.73.
193, right?
1.73.
Oh, negative 1.73. Okay. Okay. Okay, so if you take it to 4 digits, would you also have 19?
Yes.
Yes. Okay. So let's use that. Anyway, we can't even do that because of the table. So yeah. Okay. So this is the Z value, right? For these two. So we are going to go to the table to find these 2 values, right? Going to the table now. Right. So recognize that these Z values are equivalent to the Z1 position and Z2 position, right? So when you find them on the table, they will be the bound for this area, just as we showed before. So if we go to the table very quickly, we'll see that the area for Z of 1.7319 will be equal to, let's look at that, positive 1.7. So we're looking for 1.73. That is the most we could go, right? So this is 1.7, and we go underneath 0.3 to find the intersection. So we are looking for this value. Right. So we got the area of 0.0418. Okay. 0.0418. Let's go back to the question now. So 0.0418. And we also find the area that is covered to the left tail for Z of negative 1.7319. And again, we can only go as far as negative 1.7. Oh, okay. So this value was gotten for negative, right? So that's what we did. So we had 0.0418 for negative 1.73. Okay, so let's move that down. This should be for this. Okay, so let's look for the positive one. So we're looking for positive 1.73. Right? So positive 1.7 underneath 3 will give us 0.9582. So we have 0.958. Okay, so the area of interest will be what you get if you subtract the area of Z of 1.7319 and subtract the area of Z of negative 1.7319 from that, right? Okay. All right, so if you subtract those two areas, we're dealing with 0.9582 minus 0.0418. And that will give us seems up to 0.9 something, right?
165.
9165, thank you. So that is what we have, right? And so notice that even though the bound is the same from 12.5 to 13, the probability of getting the average of 12 people to fall within that range is much more bigger, right? I mean, this is like 38%. This one is almost 91%, right? Almost 92%. It's bigger because you are dealing with a larger number of people, right? But the other one was just one. Okay. All right. Any question on this one? C up to on A up to D. Okay, so I wanted to edit this out, the question E, but I couldn't because these things are preset. So, but let's go through that very quickly. For E, it says for part D, which is the one we have here, is the assumption that the distribution is normal necessary, right? So if you remember the central limit theory, we're essentially saying, see this slide? Yeah, I think so. We're essentially saying, it's not here. Okay, it's not on this slide here. We're essentially saying that when the sample gets to 30, its distribution becomes normal. So you check your sample size, we have 12, right? So since it is less than 30, and you're answering this question using a table that denotes a normal distribution. So the only way you could have made that jump from working on a data that is less than 30, which may not be normal, to one that is normal, is that you assume normality, right? So for this question here, question E, if the sample size is less than 30, yes, you have to assume normality. So the answer here will be yes. Okay. But if the sample size is more than 30, it's already normal, so you don't need to assume it. So that's I'm not going to be bothered about that question. I wanted to take it out, but that is how to respond to that, right? So whenever your sample size is more than 30, it's already normal, so you don't need to assume normality. But if it's less than 30, then it is. Like, it may not be normal, so you need to assume that it's normal before you buy it. So if it's less than 30, the answer is yes, assume normality. If it's more than 30, then just the answer will be no, you don't need to assume normality. Okay. All right, so let's go to the last one. It says find the IQ. Find the interquartile range for the average first time working age of 12 people. So pay attention to this one also. So this question is referring to the average of 12 people, not one person, right? If it's the average of one person, then we're going to be using the first distribution. So standard deviation will be 1. And it's talking about the average of 12 people, so we're going to start using the standard deviation of 0.001. 288 to solve this question, right? So once you observe this concept, these principles, I'm sure you did. So let's look at question F. So you want us to find the interquartile range, and the interquartile range is simply Q3 minus Q1, right? So we just get the answer for Q1 and Q3, subtract that to get the final one. All right, let's move all the way now. Any question or concern on this? Okay, let's move all the way down. Let's move this down again. Hopefully they are staying together. So let's go ahead and look at question F. Let's use green. So for question 12, they want us to find the Q1 as the first thing. So if you check this way, assuming your Q1 is here, and we know that Q1 captures the 25th percentile. Right? So we know that the area given. Now, because we said before that whenever the question mentions area or percentage or proportion, we are talking about the same thing. So when this question talked about Q1 being 25 percentile, we know that that is area. So we know this is 25%, which could be represented as 0.25, right? So the question is simply, what is the value here? What is the data point here? Okay. We know we can't find the data point directly. We're going to get the Z value first. Okay, so let's call it Z2 to be consistent. So if we find this value, then we can change it to the data point, and that will be the answer for that location, right? So let's quickly do that. We have the area of 0.05. So we go to the table to know what value of Z captures or bounds this area of 0.25. So let's go to the table quickly. We're looking at the normal table again. We're looking at 0.25. So we are going over here. 0.2 is over here. I'll just go through the first column, right? If I get close enough, I can move some. So 0.24 is here, 0.27 is here, which means I have to come back here and move all the way until I get 0.25. Okay, so it's like I actually have to go to the next column here. So this is 0.25 here, but it's more. This is the closest. It's lower. So we are picking a Z value of negative 0.6 under the column of 8. So we have negative 0.68 as the Z value associated with that area of Q1. So the Z value here is negative 0.68. Okay, but we know that this is not the value we are looking for because the question wants the answer in the data form. Okay, so converting it, we know that Z is giving us your data minus mean divided by standard deviation. Okay, but you remember the standard deviation you're going to be using will be the central limit theorem, right? Because that question is talking about 12 people. So we're going to be using that instead of just standard deviation. So here we know that data Z we just found to be negative 0.68. We are looking for the data point. We know that the mean is 13. And we know that the standard deviation that we are supposed to use here is 0.2. The one that has to do with central limit here, right? Is 0.2887. So over here we have 0.2. Okay. Time is moving too fast. So if we solve this equation algebraically, you find that your x is negative 0.68 times 0.2887. Whatever you get there plus 13. Right? Okay. Help us with this one.
12.80.
12.804. Thank you. Anybody having a different value from this? Let us know, please, if you get a different value. So that is Q1, and then Q3, of course, will be the area shaded to the 75th percentile, right? We know that the area bounded by Q3 is 50%. So this would be 75%, right? And that is equal to 0.75, right? So to find the data point that is there, we need to find the Z value that is there first. Let's call it Z1. So again, we go to the table and find the area that is at that point. I mean, the Z value that is at the area of 0.75. So go back to the table, look for 0.7, should come over here. So this is 0.75 over here, but we want the smallest. So let's keep going. This is increasing. So let's come over to the next. So this is 0.75 here, but it's slightly bigger. So we go to this smaller one. So we have this value, 0.74. Is the closest we can get. And we found it at 0.6 under 7. So this is Z value of 0.67, right? Okay, so let's go back to our worksheet. So we know that the Z value we have here is the Z value of 0.67, okay? But again, we need to convert it to the X equivalent, and we are using the same formula. We know that Z is equal to our data point minus the mean divided by standard error, right? Because we are dealing with central theory. But assuming this question has said, instead of 12 people here, assuming the question says one person randomly selected, right? Then we would have been using the standard deviation one. Right? So take notes of that. So again, we are using the standard error and not just standard deviation. So we have here the Z value of 0.67 is equal to, we don't know the data point, we know that the mean is 13, and we know the standard error will be 2887. So just as before, if you solve this algebraically, you have 0.67 times 0.2887, and you are going to add 13 to that. So please also help us with this one.
$13.193.
13.193. Thank you. Anybody getting something different? Please let us know. So in some sense, this question is like the previous two we solved, right? It's just similar. So we find this area, we find this area, the bigger one and the smaller one. They're asking us what is the difference between the two. So we know that the last part of that question, IQR, interquartile range, is usually given as Q3 minus Q1. Okay. And we know that Q3 here in terms of the data is 13.193. We subtract Q1, which is 12.804. And that will give us the answer to that question. Okay, any concern about this one? Can somebody help us with the final value again? 0 point something.
$0.239.
0.239, thank you. Okay, so any concern about this question? That took a while, so let's try to move faster. So we've taken care of that. Still have a couple of, we hope we'll finish them today. So let's look at the next question. This has moved. All this down. Excuse me. So the next question says, assuming the population, okay, assuming the population has an approximate normal distribution, okay, that's the way we would have said, assuming a population. If a sample of 18 has a sample mean of this and a sample standard deviation of this, find the margin of error at this value, okay? So I think at this time I should just go to the slide and introduce just that a little again. we were discussing how to differentiate between when to use Z and T, right? Notice that in the question we solved just now, we were not bothered about it, right? Because the central norm limit theorem is assuming a normal distribution. So we're solving those questions without bothering about whether we're going to use Z or T. But in this section right now, calculating the critical value, calculating the margin of error, you will need to be sure of which one to use. And I tried to show the difference between them with this simulation. I was able to open it today, so I can run that for you. Okay, so if you plot your usual normal distribution, this here is the normal distribution, right? What you're seeing, so these are normal distribution. But the remaining four functions will be plotting the T distribution. But what I've done is that I keep changing the sample size. So if the sample size of 1 is the first one we're going to plot, and it's going to be red in color, it's a T distribution. But see where it appears, right? It's just the same shape with the normal distribution, but the tail is somewhat fatter, right? It's raised up a little bit. Now, if you keep increasing the sample size here will be sample size of 3 because DF is 2, DF is n-1, remember? So if I plot that next line, it's going to appear in green. I've got the sample size has inched up a little bit. The shape is inching up towards the normal distribution. It's coming closer, right? The peak is coming up to join the normal and the tail is flattening out. If I keep increasing the sample size, let's plot the next one. The sample size of 6 is going to appear in blue. So all these colors are all T distribution of different sizes. So, but you can see as the sample size for the T distribution is increasing, it's becoming more and more like the normal distribution. So I'm going to skip now and jump to 30, where we have the central limit theorem saying that the distribution will become normal. So DF of 29 will be equivalent to 10 sample size of 30, again, because DF is n-1. So if we plot that last column, it's going to appear in red. You will see the red cover the black line, because it's kind of almost the same thing, right? So you see the second red laying almost over the black line, right? So what in essence is this is telling us is that above 30, your T and Z distribution kind of becomes similar, very similar, right? But this is rough approximation, okay? This is a very rough approximation. So there are rules. Some textbook we say, hey, if the sample size is up to 30, just go ahead and use C all the time, right? But we know in reality that computation will still be off, because if you look at this shape here, you see the second red, it's not perfectly the same thing as the black line, right? It's close enough, but it's not perfectly the same thing. So because of that, if you still implement that rule 30 and above, you're still going to get an answer that is close enough, but not perfectly correct. Okay, so we're trying to be as correct as possible. So there's a different rule guiding that, right? Presenting for you in the class. And if you work on the textbook, you might see 0, you might see 30 and above, you see, right? So different authors will say different things. And the problem we have with textbook is that there's no way you can adopt a textbook that agrees perfectly with what you know to be the current theory in the field. Each textbook gets updated at the time. Okay, so we are using here our decision for changing or choosing either Z or T. We are using the population standard deviation to make that decision, right? So whenever you know the population standard deviation, go ahead and do a Z. When you don't know the population standard deviation, don't worry about the sample size, just go ahead and do a T as well, okay? Again, I will go back to the system and correct your answers. And everyone had been corrected up to chapter 7. So unit 7 at the end of the week, we can correct that as well, okay? But your answer should not be very far off. It shouldn't be more than 1 unit bigger than the actual answer, okay? And sometimes they will match, sometimes they will not. All right, so this is what we have. And then if you go beyond that, this is your margin of error. Okay, and I think I want to talk about the formula expanded. So this is the formula for, let me pick up. This is the formula for confidence interval, right? It's just you're trying to estimate the population mean, right? and you ended up getting a sample mean, but you know that it could be off because several people will get different sample mean. So you are subtracting an error and adding an error to make a two band of where you think your answer should lie. Okay. So if you break E down, E, the margin of error, is defined this way. Okay. Do anybody recall what this one is called? If I circle this, what is this called? Just this one alone, the one that I circled already. Is related to the confidence level. Just the one already. So let me also circle this side also. Okay, so one is T, one is Z, right? Okay, that might be a couple of classic, but this is called the critical value. So remember our margin, this is how it's related to the confidence interval. So if I have this and I decide to pick, let's say 95% confidence level, the value here and the value here are my critical value. They are the critical value because they are the value that let me make decision on where the 95% stops. Okay, so this value here could be a Z. This one is negative, this one is positive. I could be a T. This one is negative, this one is positive, right? Depending on whether you know the population standard deviation or not. So these are called the critical values. Okay, so what I circled here is the critical value. Okay, so it's the critical value times the standard error. Now you see the margin of error. Okay. But we are saying, when do I use a T? I use a T when I don't know the population standard deviation. But whenever I know the population standard deviation, I should use this. Okay. Let's say something. Okay, maybe I'll remember later. So that is what it is. Okay, so see that this expression is in positive form, right? Even though there could be a negative Z and T, they are all written in positive form. So whenever you're calculating critical value, be sure to do so in positive terms. Okay. Okay, so let's go ahead and apply this knowledge now to solve that second question. The critical value and the margin of error. Okay, please. Okay, so what this question is asking us to do is to find the margin of error, right? I can as well have broken it down to two questions. I could have broken it down to say, okay, find the critical value first, and then find the margin of error next, right? Because you can't find the margin of error without finding the critical value, because those, the first one is part of the second one. Okay, so let's go ahead and look for the critical value first. So we scan the question to see if we have population standard deviation. What we have here is sample standard deviation, right? So if it's sample standard deviation, then I should use T and not C, right? Okay. So I'm going to go ahead and do T here, match critical value. So we're looking for question A, we're looking for T alpha over 2. These are critical values. So if we're solving this, yes, please.
Wait, so do we use T when we know the standard deviation? I'm confused. Or do we use C since it's given us?
Yeah, so it gave us the sample standard deviation, right? So we use Z when we know the population standard deviation. So this is, I didn't write that in full, but this is population standard deviation. That is the symbol, right? Okay, so whenever we know the population standard deviation, we're going to be using Z. When we don't, so look at the formula. So here you have population standard deviation, but here you have sample standard deviation. Okay, all right. And so when the question says sample, we know it's sample. If it's population, it's going to also say population standard deviation. So let me write that notation here. This is for population standard deviation. And this is sample standard deviation. Okay. So That's the notation. So we are looking for the T here because we are dealing with samples. So the first thing to do, of course, is to get your alpha over 2. So let's try to get alpha. If you recall from previous classes, we said alpha is 100 minus confidence level, right? The confidence level in this question is 80. So we know that alpha is 100 minus 80, okay, which will give us 20%. Right? And we're looking for alpha over 2. So alpha over 2 will be 20% divided by 2, which will give us 10%. But we know we are going to be using a table and we want this area in decimal. This is equivalent to 0.1. Okay. And so remember that I've divided alpha by 2. So what I know here right now is the area to 1 tail right is 0.1. That is the area of interest. So I'm going to go to the T table to find out this critical value using the area of 0.1. But we also know that on the T table, we need the degree of freedom. If it's Z table, we don't worry about the degree of freedom. For T, we need degree of freedom. So degree of freedom is n minus 1. So in this case, we have a sample size of 18. Subtract 1, we get 17. So our degree of freedom is 17. So if we go to the table, we are going to be interested in using the area 0.1 and degree of freedom 17 to find the T critical value. Okay. So let's go to the T table. Okay, so there is the T table. I remember that the area we have is 1 tail, right? Because we divided it by 2, so we are getting only 1 tail. So I'm going to go to look for the area of 0.1 on the T table. So remember the area is on top here. So we're looking for 0.1 along 1 tail, right? So we find it over here. So this is 0.1, right? That is 1 tail, right? And we're looking for the degree of freedom of 17. So we go over to 17, which is here. So if you move along this column to this point, this is your item of interest. That is the Z value you are looking for. Positive 1.333. Okay. So come back here to the shade, and we know that our critical value here, and our T critical value, T alpha over 2, will be equal to positive 1.3. I hope that is once. Right. Any question on how we got this? So once you get your critical value, now you can solve your margin of error, right? The margin of error some use ME, some use E, it's not a standard deviation. It's given as the critical value times standard deviation, sample standard deviation divided by square root of n. So I'm going to just plug in here to finish up this one. So the critical value here we've gotten to be 1.333 times the standard deviation from this question we know is 9, right? Divided by the sample size we know is 18. Okay. Somebody help us simplify this.
I got 2.8277.
2.8277. Thank you. Anybody confirming or
Not the same.
the same thing? Okay, thank you very much. So this is our margin of error. Okay, so bear in mind the relationship between all these things. So once you get the margin of error, let's go back to the slide. Any question on this one? Once you get the margin of error, okay, that's interesting. Once you get the margin of error, your E, then it's easy to, excuse me. It's easy to compute the confidence interval, right? So again, you are using is the Z critical value. If you know the population standard deviation, if you don't know, you're using T, right? So depending on your value for E, if you plug it into this formula, you can either get this extended formula, right? I simply remove for this one, I removed E, pick up the pointer. So this is the confidence interval formula, right? So if you remove E and plug in the Z equivalent of your E, then you're going to get this formula. Okay. If you are dealing with T, then you get this one, right? If you remove E and plug in T equivalent of your margin of error, you're going to get the second formula. So the two are the same, right? You just pay attention to whether you know the population standard deviation, so you're using this one. If you don't, you are using T, right? And going further, of course, the formula can be represented that way. Okay, so some notation keep it this way, or some keep it this way. They are saying the same thing, right? This is the mean plus or minus the margin of error, right? And you can separate them out. The mean minus margin of error, comma the mean plus margin of error. So let's go ahead and implement this in solving a question. Okay. Able to. Right, so let's go back to the worksheet and pick up the question. And I think we should solve maybe this one first before this. But this will take a little time. And we did something like this last time, but we'll try to do it using time. Okay. I think my questions are messed up, but let's see if I'll be able to out there. Okay, I will try to arrange them as we go. Okay, let's take care of this one first, right? This question says, assuming that a sample is used to estimate the population mean, right? Find 95% confidence interval for a sample size of 47 with a mean of 58.7 and a standard deviation of 12.2. Enter your answer as an open-ended parenthesis. Let me see the next question. So this is going to be T. So what we're going to do here to get practice for Z and T, let's change this thing here to population standard deviation. Okay. So in place of sample standard deviation, I'm going to change it to population so that we can get practice for doing confidence interval for Z and confidence interval for Z. So let me assume this is population. Okay, I think it's 21.2. So let's assume this is scratched out, and in place of it, what you actually have is a population standard deviation of 21.2. Okay. So if population standard deviation is given to us, they're asking us to find the confidence in 95% confidence interval, right? Okay, so essentially they're asking us to find this formula. This is what they're asking for. What is the value on the lower and the upper end? They want us to have that in parentheses. Okay. So you want to take note of everything. The mean is very clear. The mean is 58.7. So I don't need to work that further. I'll just go ahead and get our E, right? So E could be a Z or it could be a T, right? So looking at this formula, because we know the population standard deviation, and we know this will be a Z. So I'm looking for Z alpha over 2 times population standard deviation divided by square root of N. This is my E. So once I get it, plug it in there, remove it from the mean, you have the lower band, add it to the mean, you have the upper band. Right? Any question? Okay. So we move ahead to solve this very quickly. So Let's do it in parts. Let's get the critical value first, right? So let's first of all get the critical value. Let me call it I. And the critical value is Z alpha over 2. Okay, so let's try to get alpha first. You know, alpha is 100 minus confidence level. And in this case, our confidence level is 95. So our alpha will be 5%. Okay. And if I get alpha of 5%, I'm interested in alpha over 2. So I'm going to divide that 5% by 2. And that gives us 2.5%. Right? But I know we want it in decimal point because we're going to be using the table. So let's change this to 0.025. So that is our critical, that is our alpha, not the critical value, right? So I can go ahead now to get the critical value. So this will imply that our Z alpha over 2 will be the value of Z that is equivalent to this area in the table. So we go to the table now. This is Z table. We're looking for 0.025. This is 0. Okay. So this is one way to deal with this question. Okay. And I will show a second way because you want to bear in mind that your final answer here must be positive. Okay. So if I look for this area, I'm going to get a negative value, but I need a positive value, right? So another way to look at that is to say, okay, if I'm again looking for Z alpha over 2, I'm trying to get alpha. Okay, I've gotten alpha actually. So I'm trying to get that Z alpha over 2 should mean the same thing as Z of the value I have at 1 minus alpha over 2. Okay, so that will be Z at the value of 0.025 minus 1, or rather 1 minus 0.025. Okay, so that will be the Z value that has the area of, can you help me with this?
0.975.
0.975, thank you, 0.97. So if you look for this area, you're going to get the positive value straight, but if you look for the first one, you're going to get the negative value. But bear in mind that the margin of error is a positive number. So the value you're going to be using for critical value here in this computation, everything must be positive. Okay, so let's go ahead and look for 0.025 first before we look for 0.975. I'll go to that table again. 0.025 will be over here. 0.028 is here, 0.022, so it should be somewhere here. Okay, so 0.028, so this is 0.025 exactly, right? So this value is found under 1.9, negative 1.9 under 6, right? So I have negative 1.96, that is Z value that is equivalent to that. So I know that my critical value, which is on all of this, is given as negative 1.96. But because you're doing margin of error, you quickly pick the positive value of this to use in this formula, okay? But another way to avoid that is to solve it the way we solved here. So if we are looking for the area of 0.975 instead of the area of 0.025, you're going to get the positive equivalent. So let's go to 0.975. Because we know where it is already, we can easily trace it. Go to 1.96 under 6. So you see it right here, right? So the positive value here is for the area of 0.975 is also 1.96 under 6. Sorry, on 1.9 under 6, which is 1.96, right? Okay, so if we do that, the critical value we have here is 1.96. So if you do the negative, remember you're using the positive. If you want to work with the positive, that is fine. So we go over here to put in the value. We know that our margin of error is going to be 1.96 times the population standard deviation, which we know from the question to be 21.1, divided by this square root of sample size. And we know that the sample size is sample size of 47. Right? Or be the answer again, please.
6.061.
6.061. Thank you. Anybody getting something different? I'll go ahead with this one. Okay, so once you got your margin of error, you are really done, right? Remember, the question is confidence interval, not margin of error, but I've broken it in part this way, so you pick up the concepts. So first of all, we solve for the critical value, and when we got the critical value, we combine it with everything to get the margin of error, right? But the formula we're interested in is this one. You already have everything you need. So to calculate the confidence interval, we are simply going to be saying, okay, for the lower one, you are supposed to have the mean, which we know here to be 58.7, is given in the question, right? 58.7 minus the margin of error, which is 6.061. That will give me the lower confidence interval. The upper one, you have 58.7 plus the margin of error, which will be 6.061, right? So if we solve this, can you all help us subtract and add, and let's get two values here.
And 52.639.
52.639 at the lower part, right? And the upper one, 60 something.
64.761.
761. All right, so those are the two values we need. Those are our confidence interval, this here and this here. Okay, but see that we've done it in parts, but this is the simple formula, but take note of how to do the critical value, then do the margin of error, and then put them together to get your confidence interval. Okay. Question on this one. Okay, I'm going to move ahead to do the next question on sample size, complete sample size. That is a new concept we've not really covered. And then we see how much time we have. We can come back with this one over here. Okay. So let's say we are dealing with this question. I think this one should come down this way. Maybe it didn't. Let's say we are dealing with this question. It says you want to obtain a sample to estimate how much parents spend on their kids' birthday, right? Based on your previous study, you know that the population standard deviation is approximately 36.1. So you're also given the symbol telling you it's population standard deviation, right? You would like to be 90% confident that your estimate is within $1.5 on average of what was spent, right? So lastly, on the PowerPoint, that's the only slide left, is this formula here. So this is the formula for estimating your sample size, right? When you know the margin of error, that is the formula. And so you can see they are emphasizing the positive one, 1 minus alpha, or 1 minus alpha over 2, as the case might be. That is the positive critical value. That's the formula is emphasizing. So let me go back to that space. And you know that stuff, that equation was gotten from the margin of error. Remember the margin of error, let's say the Z1, because we are dealing with population standard deviation, is given by Z alpha over 2 times population standard deviation divided by square root of n. If you solve this algebraically and find the value of n, right? So it would be like, say, multiply both sides by square root of n, you're going to get this is equal to Z alpha over 2 times population standard deviation, and divide both sides by e. This we cancel out. So you're going to get that square root of n is equal to Z alpha over 2 times population standard deviation divided by e. So if you take away the square root, it will give you n is equal to, which is the formula, right? So you can actually derive it if you forget that. But since you have your cheat sheet, you don't need to memorize that. So that is how the formula was gotten from the margin of error, right? So for this question, we can answer that question very easy, right? Let me hope we get some small time to the other one. Yeah, so the sample size we need is our Z critical value. So we go ahead to get our Z critical value first, right? Z alpha over 2. That is actually the major thing to solve in this question. So let's do Z alpha over 2 first. So if we're thinking about getting Z alpha over 2, then again, we are looking for alpha, and let's go for the positive one this time, right? Alpha is equal to 100 minus the confidence level. And the confidence level for this question is 90, right? So your alpha is 10%, right? So alpha over 2 will be 5%, right? And if you do 5% to decimal, you get 0.05, right? So we're interested in 0.05, but that will give us the negative one. So let's take the positive one. The positive one will be 1 minus alpha over 2, which will be 1 minus 0.05, which will be 0.95. So it's like go to the table, find the area that is equal to 0.95, and that will be your critical value. Okay. So let's do this very quickly. 0.95. 0.95 is 97. 0.950 is here, so it's like we're picking this one as the closest, right? So if we pick this as the closest, that would be 1.6 under 4. So my Z value is here 1.64. So the critical value for this here is 1.64. So remember, whenever you get your alpha, that is not your critical value, right? Go ahead and finish up to get the value in the table. So this is the major thing I need from this question. Once I get the critical value, we can complete that. Your sample size is estimated as the critical value 1.64 times population standard deviation, right? Which we know in this question is 36.1 divided by the margin of error. They said you want the estimate to be within the margin of $1.5, right? So we do 1.5, right? But remember that everything here is raised to power of 2. So you want to solve everything inside the parentheses, then raise it to power of 2. Okay, help us here. What will be the values for this one?
Uh, 1,557.8282.
And so 1557.8282, right? Thank you very much. So take notes, This, when you're estimating sample size, it must always be a whole number, right? Because you're thinking about number of people to survey. You can't survey a fractional human being, right? So what you always do is to round up, always round up. So your final answer here will be 1558. I'll be the final result. Any question on this one?
I have a question.
Yes.
So on the homework, I used that, I had 2 of those types of problems. And one of them I used I used the exact same equation for both. One of them, it worked, and then one of them it doesn't.
And then just check through your maths. There might be a mistake somewhere.
But there's not. I've done this over 5 times.
Okay, so just send me an email with a screen of that problem, okay? And sometimes it might be that they are using T to solve the problem, right? But I'm explaining here that your decision for T or Z will always be, did you use T or Z?
I used Z because it was the population mean.
Right, okay, so the decision here for us is the population standard deviation, okay? So just send me an email with that screen.
Okay.
There could be a mistake somewhere along the line. All right, so we have 5 minutes. Let's see if we can answer the last question. We actually did this last class, right? But I thought I had a video on it. I discovered the video was not properly recorded. Okay. So, and we're gonna try to save time somehow. I don't know how we're gonna do that, but you know, this question would have been made easier if somebody calculated the mean for us and calculated the sample standard deviation for us. If we have those 2 values, then we just go back to what we just did on confidence interval, right? So the only problem here is that you're going to take our time to calculate the mean first and calculate the standard deviation first, right? because you know eventually that your formula will include those two. The confidence interval will be right. That's the confidence interval. So the margin of error you're going to do here is going to be T or C. It's going to be T, right? Because we don't know the population standard deviation. And we have a very small sample size, right? But the focus is population standard deviation. So if you expand this, what you are actually dealing with is the mean minus T alpha over 2 sample standard deviation divided by square root of n on one side, and on the other side, you are dealing with the mean minus T alpha over 2 sample standard deviation divided by square root of n. Okay, so that is what you have. So you see that you need to know the mean. You need to know the mean. You need to know the sample standard deviation. You need to know your critical value. And you need to know your n, right? In all this, you have, this is addition, sorry. So in all this, you already have your n, right? N is the number of data points. We have 1, 2, 3, 4, 5, 6, 7. So n is 7, right? We could go ahead and calculate the critical value. Okay, I believe we can do that in 30 minutes, in 3 minutes, right? So the critical value for this is T alpha over 2, right? Alpha again is 100 minus confidence level, and the confidence level here again is 95. So your alpha is 5%, right? Okay, so alpha over 2 will give you 2.5%, right? Which will be 0.025. So I'm going to look for the table, and you know you are dealing with T, so you need degree of freedom. Degree of freedom is your n minus 1, and you have 7 minus 1, which is 6 in this case, right? So you need an area of 0.02 under the degree of freedom of 6 on your T table to find your critical value. So go to the T table. T table, you need an area on one T of 0.025. 0.025 on one tail, and degree of freedom of 6. Right. So you have 2.447 as your T critical value. So we'll come over here. So we know that our T critical value is 2.447. Okay, so you've gotten that. So what you need in this piece to complete your work is to find the mean and the sample standard deviation. So because we don't have time, and we have done this over and over again, you know how to calculate the mean. Add all the data together, divide it by how many they are. You know how to calculate the standard deviation. We did that last class, but I can maybe do a video on this and post it also, right? The sum of your data minus the mean square divided by sample size divided by 1, right? So once you get this value, so let's assume the value here, that is not the value, but let's assume it is 5 here, and let's assume this is maybe 15, okay? Just for assumption. So we can plug these two values for this in the formula. So all you need to do, rounding up, is to substitute into this formula. If I should substitute quickly, then we have, let's say the mean is 5, minus, we know the critical value is 2.447. Times, we know the standard deviation to be divided by the square root of sample size. I'll give you a lower bound. It's the same thing here. It's the upper bound. I'm going to do like a 5-minute video about this for you as well. So then with this, you should be able to finish everything like this. By next class, we'll do one with it. Okay, and anyway, we have break by Monday. I'm going to be sending an email to person. Okay. I hope all these steps. So,